Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin. I'm going to cover linear transformations as matrix multiplication, and that'll help us move into composition and then also inverse transformations. So we'll start out with the theorem. It says that every linear transformation can be written as matrix multiplication. So T transformation on vector V can always be written as some matrix A times V, and what we're going to call this is A is called the standard matrix. Okay, so the reason why this can be done is through properties of linear transformations, and it really comes down to the transformation of a basis. So let's say V is written as this linear combination C1V1 plus C2V2 all the way up to Cn, which is a linear combination of its basis, the basis V1, V2 all the way up to Vn. So this is that for the vector, V in the domain space V. Now W is going to be the output vector because I'm going to do T of that vector V, which means it's going to be T of C1V1, C2V2 all the way up to Cn. Now remember the properties of a linear transformation. The transformation of the sum is the sum of the transformations, and also the transformation of the scalar multiple of a vector is the scalar multiple of the transformation of that vector. So what this will allow me to do is I can put the transformation on each one of these pieces. So this is going to be T of C1V1 plus T of C2V2 plus all the way up to T of Cn. And since now I have the transformation and these n vectors, then I can pull out all these constants to say C1 T of V1 plus C2 T of V2 all the way up to Cn T of Vn. So really what this says is since W can be written as this linear combination, and then it really says that the transformation of the basis is actually the basis of W, because you can see W is written as that linear combination of vectors. The vectors T of V1, T of V2, all the way up to T of Vn. Notice that those are vectors because the transformation of a vector is a vector. So let's call that S star. So what we know is the coordinates of V, well the coordinates of V are nothing more than these coefficients. So I can say the coordinates of V are just C1, C2, all the way up to Cn, and that's under basis S. And then similarly, since W is equal to this linear combination, notice it's got the exact same coefficients. So it shares the same coordinates, but its coordinates are over the transformed basis S, so over S star. So we're going to use this property to be able to find the transformation of some vector, assuming that I know the transformation of the basis. So what I have here for this example is the transformation. What we're doing is this is going to go from R3 to R3. So the standard basis for R3 is 1, 0, 0, 0, 1, 0, 0, 0, 1. Moving the X, moving the Y, moving the Z. So if I know the transformation of the basis, I can actually find the transformation of any general vector. So what we know is if I want to do this, the transformation. So let's say solution here. So solution. What I can say is that T of this 4 minus 5, 6, 4 minus 5, 6 is equal to T of, well, this is going to be 4 times 1, 0, 0 minus 5 times 0, 1, 0 plus 6 times 0, 0, 1. So this will add to that. Now I can use the properties of transformations. Well, the transformation of the sum is the sum of the transformation, so this is going to be equal to, I'm essentially turning it into this. So this is going to be T of 4 times 1, 0, 0 minus, minus T of 5 times 0, 1, 0 plus T of 6 times 0, 0, 6 times 0, 0, 1. Okay. Now what I can do is I can pull out these constants. I can use this property. So now this is 4 times the transformation of 1, 0, 0 minus 5 times the transformation of 0, 1, 0. And then finally, plus 6 times the transformation of 0, 0, 1. And since I know these transformation pieces, they're right here. They're right here. So t of 1, 0, 0, this is now going to be 4 times, well, the transformation is going to be 3 minus 2, 5. Minus 5 times this transformation, which is going to be minus 1, 4, 7. And then plus 6 times the transformation of this, which is going to be 2, 3, minus 6. So simplifying these things, I'm going to have 12 minus 8, 20, plus 5 minus 20, minus 35, and then finally plus 12, 18, negative 36. So what we're going to get is we'll get 29, negative 10, minus 51. All right, so leaving this up, let's prove that this can be done through matrix multiplication, and it really comes down to the transformations on the bases. So what I know is that, what's known is that t of 1, 0, 0 is equal to 3 minus 2, 5. Another way to write that is I can say t of the matrix 1, 0, 0 is equal to the vertical matrix 3 minus 2, 5. Now similarly, we had the transformation on 0, 1, 0, and we know that that is equal to negative 1, 4, 7. And let's write that vertically as well. So 1, 0, 1, 0 is equal to minus 1, 4, 7. And then lastly, the transformation on 0, 0, 1 is equal to 2, 3, minus 6. So I can say that vertically as well. So what's really interesting is if you would join these matrices, then you actually get the standard matrix for this. So the standard matrix is going to be nothing more than 3 minus 2, 5, minus 1, 4, 7, 2, 3, minus 6. And then we can also verify this. So the whole idea is that the transformation on vector v is just equal to some a times v, which is going to be equal to this. I'm going to have 3 minus 1, 2, minus 2, 4, 3, 5, 7, minus 6. And then what I'm going to do is I'm going to multiply it by this matrix here. Not this matrix. Well, I guess it is a matrix. This vector, which is this vertical matrix. And doing matrix multiplication, my goal is I'm really hoping to see this thing back. So let's double check. And what we indeed get is 29, negative 10, minus 51. All right, let me show you another way to look at this, because you don't have to really use the standard matrix. You can actually look at the linear transformation as really kind of that function notation. And let's kind of look at it this way, that t of v is equal to a times v, which is going to be equal to this matrix. And what I'm doing is I'm just multiplying by any general vector. So let's just say x, y, z, or x1, x2, x3. It's kind of your choice. So when I multiply this across, what I can see is that we're going to get this matrix. It's going to be 3x minus y plus 2z. That's just first row, first column. Then minus 2 times x, 4y, and then 3z. And then finally, we're going to have 5x plus 7y minus 6z. And if I want to write it in transformation form, like this transformation form that way, as opposed to matrix multiplication, we can just simply write it as its components. So the first component being, that first piece, second component being this second piece, and then the third component being this last piece. Which works really nicely when you're going from your Euclidean spaces. So in this case, this transformation is taking R3 to R3. So it works really, really nice in Euclidean spaces that this is, the coefficients are nothing more than the top line of the standard. Coefficients are the second line for the second component. The coefficients are the third line for the third component. So we can easily go from here to the standard matrix, and it's proved through the transformation on the basis. All right, composition of a linear transformation. So let T1 take Rn to Rm and T2 take Rm to Rp. Then the composition T, defined by, we'll say T is going to be equal to T2 of T1 of V. Very function notation, T2 of T1 of V, would be a transformation that takes Rn all the way to Rp. Let's see how this looks. So what I have is I'm starting at Rn, and what I know is that the first transformation is going to take Rn and transform it to Rm. So this is going to be Rn to Rm. Now the next transformation is going to take Rm and transfer it to Rp. So then the full transformation is going to be this. This, taking that step is going to be T1 of T2 of V. So this is going to be, that entire transformation right there. So we can see that transformation is going to start at Rn and end at Rp. Okay, so let's see what we have here. What I have is I have two transformations. I have T1, which takes R2 to R3, and then T2, which takes R3 and actually takes it back to R2 again. So we're going to see that the composition transformation is going to start at R2 and it's going to end at R2. And what I want to do is I want to compute T of minus 2, 1, basically knowing what I would have to do. So knowing that T is equal to this to this composition, okay? So what I'm going to do is T is equal to T2 of T1 of minus 2 comma 1. So what I'm going to do is I'm going to first plug minus 2 comma 1 into this transformation. Well, it says this is going to be 2 times the first component, so 2 times minus 2. And then I have 3 times the first component minus 4 times the second component. And the last one is going to be 5 times the second component, so 5 times 1. Okay, so this is going to be equal to T2 of simplifying minus 4. This is going to be minus 6 minus 4, which would be minus 10. And then finally, this is going to be equal to 5. So I performed that first transformation to here. So what we really have here is in this case, this minus 2 comma 1 transformed to this, which is going to be minus 4, minus 10, and then minus 5, if I were to say it graphically. Now I'm going to take this vector and go into this vector, and I'm kind of curious what it's going to be. It goes R2 to R3 back to R2. Let's see what happens. So T2 of this, well, T2 says 2 times the first component plus the second component. So this is going to be 2 times the first component plus the second component, so plus a negative 10. And the next second component is going to be minus 3 times the second component, minus 3 times minus 10, and then plus z, so plus 5. So what we get back here is going to be equal to minus 8 minus 10 is going to be minus 18. And then this is going to be 30 plus 5, which is 35. So that's what we get here. This would be minus 18, 35. All right, what I want to do is I want to simplify the transformation. I would like to just do this in general without using regular matrices. Not matrices, but without plugging them in. I'm going to do this with the general form. So let's say T, again, is equal to T2 of, well, T1 of V. So this is going to be T1 of x comma y. So this is going to be equal to T2. Well, T1 of x comma y is this thing. It's going to be 2x, 3x minus 4y, 5y. Now T2 says I have to do 2 times the first component plus the second component. So T2 is going to be 2 times the first component plus the second component. And then the second component is going to be minus 3 times y, which is going to be the second component. And then plus z, which is going to be that last component. All right, now I'm going to simplify this as much as I can. So this is going to be 4x plus 3x minus 4y. Over here I have minus 9x plus 12y plus 5y. And finishing this up, we have 7x minus 4y, and then this is going to be equal to minus 9x plus 17y. Okay, now it would be kind of nice to check that I get exactly the same thing. So let's do a quick check here. What is t of this minus 2 comma 1? Well, if this is the general composition, if this is the, if that's the compose, this should be 7 times the first minus 4 times the second, and this should be minus 9 times the first plus 17 times the second. And what do we get here? Well, minus 14 minus 4 is minus 18, and then 18 plus 17 is 35. So that indeed is working. Okay. Now, the next thing I want to do is I want to compute the standard matrix. Now, I already know the standard matrix. I can see it right here that the standard matrix A should be equal to the first line, and then this would be equal to the second line. We just kind of practiced this in the previous example. Just their coefficients. Now my claim is that I can actually build that standard matrix without having to do this work. I could actually have built that standard matrix using matrix multiplication. So here's kind of the idea, that if T is equal to T2 of T1 of V, well, all matrices can be written as matrix multiplication. So there should be a standard matrix for T1, there should be a standard matrix for T2. So the standard matrix for T2 should be A2, the standard matrix for T1 is going to be some A1 times V. And since matrices are associative, I can group these two first. So I can actually build this matrix A. This is going to be some matrix A times V, where A is going to be just the product of A2 times A1. Well, let's check that. If I wanted to do that, instead of going through this work, I could have actually built that through matrix multiplication because it's a little bit quicker. So how would we find A1? Well, A1 is going to be the standard matrix of this. Well, that means that the first row is going to be 2x, 0, y. Next is going to be a 3, and this is going to be a minus 4. And then next is going to be a 0x, and then a 5. Now, A2 is going to be the standard matrix for this one. Well, what we're going to have is I'm going to have two components. I'm only going to have 2 lines. But in this case, I have x, y's, and z's, so I'm going to have 3 rows. So this is going to be 2, 1, there's no z over there. But this one has a z, so this no x, a y, and then a 1. So that means matrix A, which is the standard matrix, should be A2 times A1. So this should be A2 times A1 and what we can do is we can check to see if this will actually work. Well, this is going to be this is a 2 by 3, and this is a 3 by 2, and indeed those are going to multiply because these match. So I'm going to get a 2 by 2 back, and that 2 by 2 back with a little bit of work, it's going to be 2, 3. So 2 times 2 is 4, plus 3 is 7, plus 0 is 7. So you can see that finishing this out, you're going to get that matrix right there, which is the standard matrix. So it's really interesting about composition is that the composition actually comes down to just matrix multiplication. So it's interesting that composing transformations comes down to multiplying matrices. So the very last step we're going to do is, since I can write all matrices as matrix multiplication, I can actually find the inverse transformation simply just by finding the inverse matrix. And that's just really one example, and it's a basic, straightforward idea. So we should actually look at the size of these before I move on. So what I know is that, say T1 in this case took R2 to R3. And notice what you got is you got a 3 by 2 matrix. Output, input, output, input when it comes to size. Now, T2, this went from R3 to R2. So what you're going to get is you're going to get a 2 by 3 matrix, and you can see that here, a 2 by 3 matrix. So you'll be able to determine the size of these standard matrices simply by their domain and range dimensions. Okay, existence of an inverse transformation. So let T go from Rn to Rm be a linear transformation with standard matrix A, which means A is going to be an n by n matrix, so it's going to be a square matrix. So the following are equivalent. T is invertible, T is an isomorphism, and then last, A is invertible. So we'll get to an isomorphism in another video. So let's consider this transformation. T of x1, x2, x3 is defined through this transformation. So what we know is that T of V can be written as A times V, where A is going to be this matrix. It's going to be 2, 3, 1, coefficients of the first, coefficients of the second component, and then finally the coefficients of the third component, multiplied by, our x1, x2, x3. So that's our transformation. If I multiply this, it becomes this. I know it's going to be, vertical, but it'll give you the exact same thing. So if I wanted to find, say, if I wanted to compute T of, say, -1, 3, 5, what I can do is I can plug it into this matrix multiplication. So this is 2, 3, 1, 3, 3, 1, 2, 4, 1, multiplied by -1, 3, 5. And this will spit out this vertical matrix of 12, 11, and then 15, which I can rewrite horizontally as 12, 11, 15. Now, what if I wanted to go backwards? What if I asked you to go from this, what would the pre-image of 12, 11, 15 become? Well, we did it before. I'd write this matrix with x1, x2, x3, and then plug, this thing in here, then I'd be able to solve for this. But an easier way to do that is, well, this would mean that the inverse transformation of 12, 11, 15 should be equal to A inverse times our 12, 11, 15. And we can find A inverses. We have a multitude of ways to do that. I just used my calculator and asked it to compute an inverse, and A inverse ends up being this matrix right here. And if I multiply this by 12, 11, 15, I'll indeed get back that original image, or the pre-image of this, of -1, 3, 5. So if you like the content, please subscribe.